All right, guys. So we're going to get introduced to two-dimensional kinematics here. All right. Now, the first part of this, I just want to show you again a video of what you saw in class because some of you didn't have a good look. We'll do it again in class, but I just want to make sure that you get the idea that we're talking about here. So here we see over on the left-hand side here, there's a guy that's setting up a larger version of what I had in class. So the first one, the yellow ball goes over the rod. When you release it, you saw it just drop straight down there. Okay, he's setting it up again. This one goes on the right side. You can see that it gets shoved off over the right. Okay, so now what they're going to do is they're going to set it up one more time, and they're going to put the yellow ball over on the left-hand side. That's going to drop straight down. And then they're going to put the other ball, the other yellow ball, over on the right-hand side, and that one's going to get shot off. And watch what happens. They even slow-mode it for you. Did you see what happened? I'm going to replay it here. So we're going to go back. Oh, sorry. Here we go. Playing it again. Look at that. They hit the ground and bounced off at exactly the same time. Not only that, but after they bounced on the ground at the same time. All right. The whole point of that is to show that giving an object horizontal velocity does not affect its vertical motion. The only force, once it's been shot or dropped off of that ledge, the only force acting is gravity pulling down on it. That's the only acceleration taking place. There's no horizontal acceleration, assuming that we're ignoring air friction, which of course is one of the assumptions that we make. And so therefore, an object moving horizontally will fall at exactly the same rate as an object that is not moving horizontally. They both drop with the same exact rate due to gravity. Okay, and so I'm gonna go on to an app now. I'm gonna show you in an app. We're gonna look at the velocity vectors, both the horizontal and vertical velocity vectors, the components, as an object is shot from a cannon when it follows kind of this projectile motion. All right, so follow me over there. So here we are. So the first thing we're gonna do is we're gonna shoot a ball out of this cannon. Now, a couple of things to recognize. It basically, as soon as it fires, it gives the ball some initial velocity, right? And actually, we don't have to do a ball. We're going to do a pumpkin here just for the heck of it. So it's going to shoot out a pumpkin. It has that velocity initially. All we care about is once it's been launched, what happens, all right? The first thing we're going to look at here is we're going to look at the acceleration, all right? So I'm going to click over here on the acceleration vector so that we can see that. So now watch, as it launches, what do you see? Hopefully you see a lot of boring, right? The only thing happening here, the only acceleration of the ball is the downward acceleration of gravity, right? There's no horizontal acceleration once it's left the cannon. It just keeps flying horizontally. Now, this ties into what we saw with the balls, right? The horizontal motion continues horizontally, whereas the vertical motion is being affected by gravity pulling down on it, right? And so that's what we see here is that as time progresses, that vertical acceleration there, gravity acceleration, that's the same until our pumpkin lands on the ground and goes splat. All right? Now, what I'm going to switch to is the velocity. So we're going to erase that. We're going to switch to velocity vectors. And we'll start with the total here, just so that you can, you'll get the idea. So as it fires, there we go. There you go. You can see the velocity vector. The velocity vector is changing over time, right? That makes sense. The ball shoots out horizontally, and as time progresses, it starts leaning down as gravity pulls down on it, right? This is what we saw when we were drawing those vectors in class today, right? We started with the vector this way, but as that vertical change kept happening, that vertical acceleration or change of velocity kept happening, it started pointing a little more down, a little bit more down, and over time, it does continue to point down, 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 just like that. And we get that parabolic, the projectile motion that we've been talking about, okay? Now, if we go back again, this time, instead of doing the total velocity vector, I'm going to do what's called the components, all right? So we're going to fire it. Let's pause it so that we can, so there we fire it. Notice that as we fire it, it has an initial velocity, right? It has an initial horizontal velocity. It's not going up or down because the cannon is pointed exactly horizontally. And then as time progresses, watch what happens. Look at that horizontal. The horizontal, use a ruler or something to measure it. I want you to see the horizontal is not changing. But what's happening to the vertical there, right? Before there was no vertical vector, but now there's a vertical vector pointing downwards. And as time progresses, the horizontal one stays the same because there's no horizontal acceleration, but there is vertical acceleration downwards. So the vector gets longer and longer and longer and longer and longer downwards. Now, if we add in that total velocity vector, you'll notice that that vector is the sum of the components, which goes back to that idea that we talked about in class before, that the vertical and horizontal pieces add up to give us the total resultant vector, which is what's actually happening there. Okay, so you can see that, and we continue to go, you'll notice that the horizontal doesn't change, whereas the vertical gets longer and longer and longer and longer. All right, let's try one more. We're going to actually point it up at an angle just because I want you to see what happens if we do that. Now, again, what happens when we launch it? At that instant of launching, notice that we have this this vector shooting out at an angle. We do have some vertical velocity this time because it's being shot up instead of horizontally, and we have that horizontal piece there. Just a moment, I'll click on the acceleration vector. You can see gravity pointing down there. Now, as time progresses, what do you see? Hopefully, you're seeing that the horizontal is not changing. There's no horizontal acceleration. It continues to be exactly the same. The vertical acceleration continues to be downwards. That yellow vector downwards, that's the acceleration, continues to be the same. I'm going to go ahead and take that off because it's boring. It's just pointing down all the time. Then we've got this vertical vector here. That was the velocity vector, and you'll notice that it's significantly lower, significantly shorter than it was before. And as time progresses, because acceleration is downwards, then that vertical velocity keeps changing downwards. It gets smaller and smaller and smaller until we get to the top, at which point it's purely horizontal, and then after this, we start to get a velocity vector downwards, and it gets longer and longer and longer, just like it did before. All right, so again, the point of this is to show, just like when we did the two balls, when we did that demonstration, the vertical and the horizontal are independent of each other. If two things are perpendicular to each other, they are completely independent of each other. Horizontal and vertical make it nice, but there's other situations where you have things that are perpendicular, and as long as it's perpendicular, they don't affect each other. A vertical gravity will never affect a horizontal speed, horizontal velocity vector. It will affect the vertical, which is why it changes direction and the overall velocity vector changes, but it will not affect the piece that's perpendicular to it. All right, take some time. This app is a free app. It's by Colorado. You can access it. I've put it on the website. You can go click on it, play around with it. If you get tired of launching pumpkins, you can launch cannonballs or pianos or cars or whatever you want. All right, but go ahead, have some fun, play around with it, and come with me. We're gonna go do an example. We're gonna work through our first two-dimensional kinematics example where we're having to deal with these two components at the same time. All right, let's go. All right, whoop-de-whoop, we got our first two-dimensional kinematics problem here. We're going to use that idea of the horizontal and vertical being independent of each other. All right, so here we go. We got a student using a slingshot to fire a rock horizontally off the edge of a 20-meter cliff. We're going to draw a picture because that's what you should do. Draw a picture so that it's easy to figure out what's going on. So we got it this. We've got a height of 20 meters. So we can draw that in. This is our initial height of 20 meters. And then it just says that he's going to slingshot it off the edge there. All right. Now, here is how we approach a question like this. If you recognize that this is a projectile, that it's not just going in one direction, that it's going to have both horizontal motion and vertical motion, we're going to make that table. Remember, I taught you guys to make that table for kinematics, all right? And we said, okay, we're going to put our initial position, final position, initial velocity, final velocity, acceleration, and time. Usually, we just did it in one direction because it was forward or backwards or up and down. This time, we actually have things going in two directions. We have both the horizontal and the vertical. So we're going to actually double up our table here, all right? Now, the question here is, how long will it take to hit the ground? So obviously, what I want is the time. Okay, so I'm going to label that to remind myself that that's what I'm looking for. Now I'm going to go through and write down whatever information I have, just like we normally did. So we know that it is starting right here. So we're going to define this as being, if I look at the horizontal information there, right, I can define this as being x equals 0. And then it's going to go some horizontal distance before it hits the ground, right? So I can say that's 0. Now, I don't know the horizontal distance yet. I don't know how far it goes, so I'm going to leave that blank. The initial velocity, I don't have that yet either. I don't have the final velocity in the horizontal direction. I do know that horizontally it's not accelerating, right? Remember, we saw this in that applet, that whatever horizontal velocity it started with, that velocity vector does not change. The horizontal velocity stays the same. So that acceleration for the horizontal is 0. So I don't have a lot of horizontal information right now. However, I do have some vertical information, right? I can say that it's going to start at a vertical position of 20. So I'm going to make this be 20, and I'm going to define the bottom as 0. So notice now I'm not looking horizontally, I'm now looking vertically here. I'm only looking at the up and down, not how far it goes, just the up and down. So it starts up at 20 meters, and then it ends down at 0 meters. Now, the initial velocity, this is hard because the initial velocity, we're talking about the initial vertical. I can spell vertical, I promise. The initial vertical velocity. Now, when he throws it, it says he throws it horizontally. So if he throws it horizontally, it is only horizontal. Therefore, the vertical velocity there is 0 initially. Yes, it's gonna change, right? We looked at that app, and we saw that as it had that downward acceleration, that the velocity is gonna change and it's gonna get some vertical velocity. But at the beginning, because it's thrown horizontally, it does not have any vertical velocity. The acceleration, of course, vertically is negative 9.8. Don't put that acceleration for the horizontal, because the horizontal is not accelerating at 9.8. That 9.8 is purely vertical. It's up and down in our picture here, okay? Now, at this point, we recognize that we have everything that we need except for what we're looking for and this final velocity here. So, of course, we're going to choose the kinematics equation that doesn't require us to use final velocity. So we're going to use that x equals x naught plus v naught t plus 1/2 a t squared. And we can put our numbers in, and it should look like this. Boop. And it should look just like that. We got our position in there, our initial, our final. We got the initial velocity being 0. That's nice, because that's going to make this guy actually just go away completely. And then we've got our vertical acceleration. Now notice, this is all the vertical information here, right? And so yes, it might get confusing because you're using x's there, but x, remember, that's just position. And so we're looking at vertical position here. So I only look at things that are in this vertical column. Don't look at anything else. All right. Now, from that, I should be able to solve for t. All right. So I'll give you a chance. Go ahead and pause the video, and then you solve for t. Shazam! We got time is 2.02 seconds. Now, I only had one significant figure up here. So when I write my answer here, I am just going to say, how long did it take to hit the ground? 2 seconds. Done. One significant figure. That's my final answer. But you can see how we just used the vertical information independent of the horizontal information, which then allowed us to get our answer. Okay? Now, part B here, we're going to change color. Look at this. We can go rainbow blue for letter B. Given that he launched it with a speed of 23 meters per second, how far will it travel? All right, so they just gave us another piece of information, right? They told us that the initial velocity was 23 meters per second. I'm not going to put the units in there because I've got everything in SI right here, right? So I've got 23 meters per second. Now, notice that I do have a time now. This was the time that it took to get to a vertical displacement of 0, a vertical position of 0, which is down at the ground. And so that's exactly what I'm looking for. How far will it travel before it hits the ground? So this time is going to be that 2.02 that we found in that first part, okay? And so we now have enough information. looking at what we have here, right? We do not have that final position, but that's what we want. And so that, remember, we want to put a variable there to remind ourselves that's what we're looking for. How far does it travel? We don't have velocity again. So again, it looks like we're going to go into that same equation, but this time we're using the horizontal information. So we're going to use x equals x naught plus v naught t plus 1/2 a t squared. So again, we'll put in those numbers. We know that x naught was 0. That was given to us right here. And then we have our initial velocity, which was just given to us, 23. The time being 2.02 seconds plus 1/2. And this isn't going to matter, obviously, because the acceleration is 0. And you notice that those two terms go away. All you have to do then is multiply 23 times that 2.02, and we get an answer of 46.46. Now, again, 46.46 meters, but we only have one significant figure here because the time only has one significant figure. And so our final answer is going to be that it travels approximately 50 meters. Now remember that 50 meters means that it can be anything down to 45 or anything up to 55, right? Because it's one significant figure. The second digit can be anything that's going to round to that value. And so that's why we're okay with writing our final answer as 50 meters. There you go. We've been able to solve this problem with two-dimensional kinematics. Remember, the important thing here is that you are keeping the vertical and the horizontal separate. You can't put them in the same equation. You can't put them in the same column of your table. And if you keep them separate, then you're going to be A-okay from here on out. All right? Check out the next couple. They're going to give you a couple more challenging questions. All right? See you next time.